In review 3, we're going to be looking at two different things. From chapter 6, we'll take a look at distributions, and from chapter 7, we'll be taking a look at probability. With distributions, there were three main things that we were looking at. That would be the shape, the center, and the spread of it. Now, at the very beginning, when we started looking at distributions, there were different types of graphs that we would look at. Like we did see some examples of things that were called bimodal. There were some examples of things that were called uniform. But for the most part, what we did in our coursework was start to focus our attention on graphs that would be called unimodal. That means that they would have one high bump that goes along with them. Now, with the unimodal graphs, the basic shapes that we got were either symmetric or they would be skewed to the left or the right. Okay. The first questions that we're going to be looking at on the review, so problem number 1 here is just going to be about the shape there and whether or not we should expect the description that's given here to create a skewed graph or a symmetric graph. If it is going to be skewed, you are going to be responsible for identifying what direction it's going to get skewed to. As a reminder, the direction that it gets skewed in depends on if we have outliers in that direction. So if you have high values that are outliers, that will skew it to the right, it skews it into that higher direction. Okay, and as you're answering the questions, that tends to be the main thing that you're looking for here is when you read the descriptions, think about whether or not you do have the potential for skewed values. Now, pretty much every example that you look at, you're going to be able to tell yourself that there are going to be high values, that there are also going to be low values in there. But what you really need to think about is there a potential to have high values and not low values? That creates the skewness. If you have high and low values, they actually balance each other and they give you that symmetric graph. All right, so let's take a look at the very first problem. If we were to make a distribution for the age at marriage of women in the age at first marriage for women in the United States. When we do start, so you can probably imagine like what would be a common age for this, right? For a woman to get married the first time is probably going to be most likely in their mid-20s. Okay, you may have an opinion that it's closer to 30. It kind of depends just on your personal, I guess, experiences on this, which you might believe. All right, but if you take a step back and you look at all the ages as a whole, one thing that's absolutely true is that you're not going to have really young females getting married. I mean, we shouldn't be. I don't know all the laws on it, but I would assume that most of the laws are around you can't get married until you're 18. Okay, so at 18, we start seeing marriages might start to increase in the mid-20s and the 30s. But then if you start to look in the older age range, there is a potential for a woman for the first time to get married in her 50s. She may have been single all the way up until that age, and then she gets married there. So there is a potential that we do have outliers, values that we don't really expect on the high end, but we don't have the potential for very low marriage ages, right? We think the typical one might be around 25, 30-ish range. You can't get that much lower than that, but you could have the potential for ages that are much higher. All right, so this is going to be skewed right. Okay, most marriages, so this is what I wrote down, most marriages probably around the 20 to 30 range, but you can have older women who are getting married for the first time. All right, B, the daily snowfall in Omaha in January. For this, it's going to end up being symmetric. Again, we're going to think about outliers. In January, is it possible that you can have some days where you have a lot of snow and you have some days that don't have a lot of snow? The answer to both of those questions is yes. You can have some days have more, some days have less. However, when we think about the days that have more versus the days that have less, they're probably going to balance each other out. The other thing here is we're choosing January, which is right in the middle of winter. We're not choosing a month that's on the cusp of winter and spring where you might just have this one crazy day of a lot of snow, which would be an outlier. So in January, we typically believe it's going to hold to be consistent. You are going to have some variation here, but not a whole lot. And symmetric graphs do have variation. They do, they got that bell shape that tapers off in the high and the low part of it. Okay, but we shouldn't expect any true outliers in that. C, scores on a very easy test in which a perfect score is 100. The fact that we have an easy test here is kind of indicating that most of the scores are going to get close to that 100, but they're going to get capped in that direction as well. So it's sort of like the age of first marriage. That one's going to get capped on the bottom end at around like the age of 18. I'm just assuming that'd be true. The scores here are going to get capped at 100. Like, no matter how great somebody does, the highest score that they can get is 100. Okay, so we're bounded on that end. However, and because it's an easy test, we also expect the grades to probably be in the 80, 90 range sort of deal. We don't expect people to flunk the test if it's an easy test. However, there is the potential that people can do bad. And from my experience teaching, that is a very common thing that I'll have. A lot of the tests that I give, most students do pretty well on them, and they're in the passing range of it. But there's always going to be a few students that have not participated in a class. They haven't done any of the studying, and for some reason they think that it's still going to work out. And they take the test and they get grades of like 20s or 30s on them. So those would be outliers, and that would give you a skewed left, because most of our scores are going to be the high end, which is the right. That's going to be your big mound. But then it's going to taper off to the left where you got those low scores approaching the zero score. All right, so in question number 2, we're going to move away from that subjectiveness that you see in question number 1, and we're going to take some actual values and we're going to create a normal distribution and answer some questions about that. The prompt to the question does say that we have some information that is normally distributed, so that's what's going to give you that symmetric looking graph. And you're going to be provided a couple pieces of information. One is going to be the mean. Okay, the mean, so here we're looking at GRE scores, and the mean is going to be 152, and the standard deviation is going to be an 8.9. Oh, this is for the quantitative section, which is the math section of the GRE test. If you are not familiar with the GRE test, just sort of think of it as being like an SAT test, and that'd be fun. All right, on your normal distribution in the dead center here, all right, that one matches up to that high point there. In the dead center is where you're going to put your mean, which is the 152. So you're not going to have to calculate this. This would be provided for any problem like that. So you get the 152 there. The 8.9 is your standard deviation. You're going to add 8.9 to the right to create all these increments. So every time you see a little mark here, that is going to represent a standard deviation. Okay, so if we increase 152 by 8.9, we get 160.9. That takes you out one standard deviation in the higher end. You can also subtract the 8.9 to get the 143.1, and that gives you the lower, well, one standard deviation in the lower direction. You continue to do that all the way out, a total of 3 times. You go out to 3 standard deviations. You can technically go out further. You could do more, but there really isn't a lot of value to that. And the reason is because in any normal distribution, if you look, let me get some little papers here to guide this. If you look within 1 standard deviation of your mean here, that's going to represent 68% of the data. It's not exactly 68%, but it's super close to it, so we always just say 68%. If you go out to 2 standard deviations, you've actually covered 95% of the data. We expect that 95% of any information we get about these math scores is going to sit between those 2 standard deviation measurements. I don't think they came out right, but within 2 standard deviations of the mean. Once you go out to 3 standard deviations, I mean, you can look at the graph and see it almost appears as though we have the entire graph at the point, but it is going to represent 99.7%. So you still got 0.3% that go out into the sides here. And being that it is symmetric, that means that you'd have, I think it's 15 hundredths. It's half of 0.3. That'd be that direction, then half of it that goes that way. So we only draw the graph out to 3 standard deviations because there really isn't a need to go beyond that. All right, so you begin by taking the information and just building the whole thing. Now remember the rule, it's 68, 95, 99.7. Those are your main checkpoint values there. All right, and then what we're gonna do, Actually, I was about to get a little bit ahead of myself. The first question is going to rely on that. The other two questions are going to rely on values that are not actual increments that we see as standard deviation measurements. Okay, so B says, complete the statement about 95% of the quantitative scores are between blank and blank. Well, if you know these rules, then it's pretty easy. You just go out to two standard deviations and you take those two numbers that you had and put them in the blanks. And that ends up being it for that problem. There's a whole bunch of other questions that we could ask using that. Definitely go back through the practice work and look at the different types of questions where we might ask you what percent did better than 60.9. So if we ask that question, what percent did better than 60.9, using these values, you can actually break it into left side and right side percentages and answer the questions. But on the review, that's the only question that I'm sharing with you. All right, C and D, these are going to get into values that would not be located at standard deviation checkpoints, so not these numbers here. And we talk about percentiles, we also talk about z-scores and these things. Okay, so it says approximate the percentile of 160 score. Okay, so 160 score is going to be right below that. Okay, it's going to be right below that. And when we say a percentile, what that refers to is if you got a score of 160, what percent of everybody else who took that same test did you do better than? That's what it's suggesting here. Okay, so right here at 60.9, if you were to use these values, and I know we talked about this in class, so I'll do it a bit faster. Up until the mean, that's 50%. Going out one standard deviation is going to be half of 68, which is 34. So if I add 50 and 34, I'm going to get 84. I'm going to get an 84 percentile. However, in this question, you're not right there at 60.9, you're just in front of it, which means you're going to get an answer that's a little bit lower than 84%. And you can see that answer right now is, it's about 82%. I didn't round it because I took the value from the table, but it's about there. Okay, so now how do we get that value? You're going to do easy calculation, then you're going to go to a table of values and you're going to look up a number. Okay, we start with a value that we're interested in, which is 160. We're going to subtract the mean, the 152 that was given at the beginning. You're going to subtract the 152. That difference, you're then going to divide by 8.9. Now, when you do this calculation, it's a really short one, but make sure that you do subtract this and you evaluate that part. You press equals, you press enter first before you divide it. Because depending on what type of a calculator you're using, if you try and type it all once, it doesn't quite work. So make sure you do subtract first. Once you do that and you divide, you're going to get this number, 0.899, which is basically 0.9, let's say 0.90, because that's how you're going to see it on the table. Okay, this is what we call the z-score or the standard score. It represents the number of standard deviations that value is from the mean. So remember when we go up here, the mean's in the middle, and I compared it to this value, which would be at one standard deviation, but 160 is slightly less than that. It's going to be just inside of it. So that's where you're getting 0.9 standard deviations. One standard deviation takes you to that point. 0.9 standard deviations is going to take you just a little bit less than that number. Okay, so now that we got that number and we even compare it to the graph to see that it makes sense, we'll go to the table. All right, so we have a z-score of 0.9. Here's your z-score of a 0, and then these are all your positive numbers here, and then these are all your negatives if you're to the left on the graph. Z-score of 0.9 is down here. Okay, so 0.9 is going to correspond to a percentile of 81.59. Okay, now if you get a z-score that sits in between a couple of the numbers, take whichever one is, like whichever z-score is the closest one, you can just take the percentile that goes with that. Or if you want to just sort of estimate somewhere in the middle, like if you got 92.92, that would be, if you had 0.92, you might want to just sort of split the difference a little bit in there. And basically, if you take any answer that's from here to there, then you'd be all right. Now, in our case, we were pretty much like on the money here that it was 0.9, so I can just take that value. And that ends up being your percentile, and that's the whole problem. All right, question D is, what if we ask you to go backwards? What if you had to be in the 90th percentile? What if you had to get a score that was in the 90th percentile? How do we do that? First, so now we're going to work backwards with the table. You're going to go look up the 90th percentile and figure out what z-score that corresponds to. Okay, so not to get confused with that 0.9, that was a z-score. Now I'm looking at a percentile. Okay, so I'm way over here. This is the closest that we're going to get to the 90th percentile, and it's pretty darn close to it. So the z-score that we're going to choose is 1.3. And really try and choose one of these. Don't get away from the z-scores that we have available on the list here. I know they only go by every 10th, but try and take the values that are here and not get too creative with them. So we'll go with the 1.3 there. All right, 90th percentile then corresponds to 1.3 standard score or z-score. All right, so now what we're going to do is we're going to take the setup, basically the same setup that we saw here with the mean and the standard deviation and the value that we would have, but we're going to make that the x value because we're solving for it. And we're going to set that equal to the z-score because then that z-score would give you the 90th percentile. So we're just working backwards. Undoing the operations, you're going to need to multiply the 8.9 by 1.3. Where is it? 8. Let's see if we got that on the screen. 8.9 times 1.3 is going to give you 11.57. That number, let's move that out of the way. That's multiplying the standard deviation to the z-score, so we get 11.57. Then to finish solving this, you're just going to add the 152 onto the other side. So you're really undoing the operations. If you subtract first and then you divide, just do everything backwards, multiply and then add. Okay, it was 152. So we're going to add 152, which is going to get you 163.57. So I'm noticing that I don't quite like the way they presented the answer, but it's fine. I rounded it off to 163.6. The truth is that GRE scores are not going to give you decimal answers, so a better answer to go along with this would just be to round it to 164. All right, in question number 3, what we're going to do is take a look at 2 sets of data, which is going to be the lengths of 9 symphonies from Beethoven and Mahler. When we're given the data here, we don't know if this is symmetric or if it's skewed. So what we're going to be doing is taking the approach of the fact that it may be skewed, and we're going to investigate it in that way. We are going to calculate the mean, which would be more with like symmetric data. But then we're also going to do the 5-number summary, and we're going to make a box plot so that we can look at a comparison of the distributions here. All right, so first off, the mean. We should all know how to do this, but you basically just add up all the numbers that would be in that data set, and then you divide by the number of items that you have there, and both of these have a total of 9 symphonies, so that's going to be the value you divide by. Just when you go through these, make sure that you add them up a couple of times, and you add them in a couple of different orders so that you can guarantee you're getting the right number here. I've just personally found that it's an unintentional thing, but you're using technology to type in numbers, and if you type something a little bit wrong, you'll get a bad total number. Once you divide it, it might not be as recognizable if you made an error. I mean, if you make something very small, like as an error, then you might not see it. So do it a couple of times, make sure that you get the right answers, add them left to right, add them right to left, do something like that. But these are the values that I came up with for their means. For the 5-number summary, one thing that's important about that is that you get the numbers in order, preferably ascending order here. In the top one, it starts, I guess in both of them, it starts to look good at the beginning because you have 28, you got 36, you got 50, they're increasing. Then all of a sudden you realize you got 33, which is a smaller number, and it would fit between these two. And then you realize, of course, they're all just out of whack. The same thing for the next data. So be disciplined. Okay, take all the values and make sure that you write them in order, least to greatest, and just do whatever you need to do to double check, make sure you're not missing any numbers. Obviously, you should count and make sure you got 9 numbers there, but maybe once you have it in a list, go through and cross out numbers just to make sure they're all matching up, because you don't want a little error based on just the fact of organizing things. All right, so your 5-number summary. I always start with the median. I was about to say mean, but I always start with the median because that is your middlemost number. And depending on whether you have an odd set or an even set of numbers, you either eliminate that or you keep it as, that's not quite right when you say keep it. But it depending on what you have at the beginning affects what's going to look like in the next step. So let's just say that we're looking at Beethoven here. You do have 9 values, which means that the median is right there in the middle at 36. Because the median was one of the values that I didn't have to split a difference on those, that value is going to get ignored when you start looking at your quartiles. Okay, so I'm going to cover up that part and say for Q1, I've got to look at the bottom half here. Now that leaves me with an even set of numbers. So Q1 is going to sit right between those two at 29. Okay, and then your minimum, of course, is going to be the 26. That's there. All right, now on the other side, again, I cover up the median. We're going to have to split the difference here, so that'll give you a 45 for Q3, and then there's your maximum at 68. And you can see all the values that I got there. Now, I'm not going to go through the other one, but it's basically the same thing because you have 9 data points. So you don't really see anything unique about it except for that ends up being a decimal when you split the difference between those numbers. So that would have been between the 85 and the 90. So you can just add them and divide by 2 if you want, and I'll give you that number. All right, once you do have these values, making the box plot should be pretty straightforward. Minimums and maximums are going to be dots. Quartiles and medians are going to be the little lines that you're going to build boxes. So you literally just take your 5 numbers and you just line them up where they should be on here, and then you create that image. I don't think there's much reason to walk through and show you step by step how that's done. You're literally just taking numbers and you're putting it, then you're making these little marks where they go. When you're all done with it, you're able to analyze it. I don't have any questions here that are going to ask you this, but you can clearly see that Beethoven's symphonies were shorter than Mahler's. Their range is not too different than each other, but you are going to see some spots where it's a little bit spread out. So like Beethoven, it looks like he may have one outlier. Yeah, he's got a 68, which is an 18-minute jump from the 50 that's before it. So if you were to take that out, that would put the dot right here, which would give you a much more compact graph and would even make it symmetric. So there's a lot that you could analyze with it. I didn't ask any particular questions here, but the main aspects are when you have small spaces, that means it's pretty dense. When you have wider areas like here or there, that means the data is more spread out because every section, 1, 2, 3, 4, every section is worth 25% of the data. All right, for the rest of the review, we're going to turn our attention to the concept of probability. So totally different than the other things that we're talking about, but here we are. For the most part, the majority of the problems that we're going to do here is going to be based in theoretical probability. So we talked about relative frequency probability, which I also refer to as experimental probability. We talked about theoretical, and in our direction here is mostly going to be in theoretical. And what that means is you basically look at all the outcomes that are available. So think about building fractions. You can see some fractions already over here. Think about building fractions, and the denominator represents all the outcomes that are available, but the numerator represents all the outcomes that are favorable, the ones that we're looking for. Okay. All right, so you have a graphic here of all the cards in a standard deck. Here, I don't have them as like colored copies of them, but yeah, the hearts and the diamonds, of course, are the red cards, and then these are the black cards. And anyway, it's kind of neat that you have a whole picture of these things, and there's a total of 52 in there. There's actually 52 pictures that we see. Okay, question A, what is the probability of drawing a spade? Well, a spade is being one of the 4 suits that we have in here. So even though we got 52 cards in the deck, you can just jump to the conclusion that it's going to be 1 out of 4. Right, you've got an equal amount of clubs, spades, hearts, and diamonds, so 1 out of 4. Now, if you want to start with larger numbers, you'd say that it would be a 13 out of 52 because there's 13 cards in every suit, and then there's a total of 52 cards. But it's going to reduce down to 1/4. All right, B, what is the probability of drawing a jack and a red card? That it has to be jack and red card. Okay, so the end situation you must meet both of the requirements for that. So there's actually only 2 cards in the deck that are going to be Jack and red. That would be the Jack of Hearts, and that would be the Jack of Diamonds. So you have a 2 out of 52 chance of drawing those cards. That does reduce down to 1 out of 26. Now for these questions, I think leaving them in fraction form is perfect. You don't need to go to decimal form for that. There's some occasions that the decimals look like good answers, but fractions for a lot of these are pretty good. All right, so C, change it up just a little bit here. What is the probability of drawing a Jack or a red card? Okay, so it doesn't have to be the Jack of Hearts or the Jack of Diamonds. It can be any red card, including like an ace or a 2 of diamonds. And it could be any Jack, including a clubs or a spades. All right, so technically what we're looking at here is what we call an overlapping situation. The thing that you want to be super careful of is that you don't think, well, I've got 4 Jack cards and I've got 26 red cards. 26 is 13 and 13. But don't look at it as I got 4 Jack cards and I got 26 red cards and then add them together and say it's a 30 out of 52 chance. Because you do have the overlapping of the 2 cards here. There's a formula that's available that says that you can add those 2 probabilities and then you subtract the overlap. But what tends to work well for the problems that we're going to be doing is to use graphics, and like this graphic is already here for you, so you might as well use it. And if you just count all the ones that fit the requirements, you're going to have the 26 reds plus 2 others that are just the Jacks. So that gives you 28 out of 52, and then you can just reduce from there. So technically that is about overlapping, making sure that you don't double count things, but having a graphic and using that graphic will pretty much make sure that you don't make any errors in that part. All right, in question number 5, the main difference that we're seeing with that question versus the last, it's still going to be theoretical probability and you're still going to be drawing something here, but the difference is that we're going to be looking at multiple events of things happening when you draw. And by saying the word draw, I don't literally mean like physically drawing something, but in this case it would be randomly generating. Okay, so what we have is situation. You're going to go for a jog, which takes about 12 minutes or approximately 3 songs. Okay. On your phone, you've got 4 rock songs, you got 5 country, and you got 1 Disney movie song that's on there. And we'll say that that's all the music that's actually saved on your phone here. Okay, so given those songs, and that's a total of 10 songs that would be on there, you're going to listen to 3 songs. So there's all these different combinations that you could get. You could get 1 rock, you could get a country, you could get the Disney. All right, now, when all these questions are asked to, these questions aren't going to be asked that the songs are happening in a particular order, just to kind of be aware of here. They're just saying, well, question A says, what's the probability that that your phone will shuffle and you'll choose 3 rock songs? Yeah, so that doesn't even have a variety, so that wasn't really what I was getting at, but the next question is going to ask, what is the probability that your phone will choose 2 rock songs and a country song? So it doesn't really matter what order they're in, it's just whether or not it's going to choose those. Okay, A, let's get back to that one. Choosing 3 rock songs. It says up here that no song will be repeated. That's an important aspect to this. Okay, so when the first song is generated and we want it to be a rock song because we're looking for the 3 rock in a row, you have a 4 out of 10 chance of it being a rock song because there was 4 of those and a total of 10 songs that were here. Okay, when the second song is chosen, because that last song is not in the pool anymore, it's not going to choose it again, the options for rock songs have now dropped down to 3. There's only 3 that remain here. And the number of songs that are available altogether is only 9 because that same song is now no longer within the draw. All right, when you move to the third event, again, your rock song is going to decrease, so there's only 2 more that are available, and there's only a total of 8 songs to choose from anyway. So the main thing about the question is that not replacing situation is going to change your numerators and your denominators. It's definitely going to change your denominators. Your numerators just kind of depend on like what type, in this case, what type of a song that we're looking at. Once you have all that, You can do the math in whatever way that you want. One of the most simple ways to do it is just to multiply straight across, top and bottom, and then to reduce that, which most calculators have features for reducing. You can reduce ahead of time if you want. For example, like the 4 and the 2, those together make 8, which is going to cancel that 8 completely. And of course, 3/9 is going to reduce down to 1/3, and you can you can get to this answer much faster if you want, but it doesn't matter. You do whatever you want. It just starts with the setup. Question B, we want 2 rock songs and a country song. Okay, so the beginning is the same thing that we got here, rock song, rock song. You're going to see the denominator decreasing. You even see the numerator decrease. But because the third song is going to be a country, that numerator is not going to follow the trend here dropping down to 2, because we still have, if we've only chose rock songs, we still have 5 country songs available. So that'll be a 5. However, the denominator has decreased down to 8 because you only have 8 songs left with the 2 rock songs that are chosen. Okay, from here, multiply across, reduce, and you get what you get from that one. All right, C, the probability that you will hear the Disney song. Okay, that means that we don't care if the rest are country or if they're rock, so you might as well pretend that they're all the same thing. All right, so the way that I approached it was to think about, well, what if we just get the Disney song first? So the order really doesn't matter, and it doesn't affect the answers at all. Just pretend that the Disney song is chosen first. So there's a 1 out of 10 probability that you'll get the Disney song. Once that is done, you only have 9 songs available. Of those 9 songs, we don't really care what we're going to get. 9 out of 9. It doesn't matter. It doesn't matter if it's a country or a rock song. It's not going to be a Disney because we've already drawn the Disney one. Okay, so you see the denominator decreasing. The numerator is actually just going to match what you have in the denominator, which means this is just 1, that would just be 1, and the whole answer ends up being 1/10. All right, for question number 6, we're going to look at expected value. When we studied this, there were pretty much just 2 cases that we focused our attention on, which was insurance policies, and that's what we're going to do here, and also the lottery problem. So as you're studying for the test, I would encourage you to look back at the lottery problems just as a little bit of a refresher, but don't expect us to go in a different direction than those 2 types of examples. All right, so for the insurance policy one anyway, here's the setup. It's very routine in how you're going to do this. There's a policy that a person is going to pay for. Oh, by the way, we're going to look at this from the perspective of the company. So the company is going to look at the $800 that they sell the policy for as a positive number. Okay, that they're going to get $800. Okay, now there's a chance that they're going to have a payout for different types of claims. They figured out that 1 out of 50 policies, a person is going to claim $6,000. They've also figured out that 1 out of 100 policies are expected to make a $20,000 claim, and 1 out of 500 will make a $50,000 claim. Okay, literally all you need to do with the problem is you start with the $800 that the policy is sold for, and then we subtract all those other values. But you subtract those values multiplied by the probability of them happening. Okay, so 1 out of 50 chance of the 6,000, so you want to multiply these. Now, if you can imagine this, another way to do the setup here, just to write it down and then to get into the calculator a little bit easier, most of these probabilities are going to be 1 out of, 1 out of, 1 out of. So you really just need to take 6,000 and divide it by 50. You got to take 20,000 divided by 100, take 50,000 divided by 500. And sometimes when I write up the problems, I literally just write it that way. I'll do 800 minus 6,000 over 50 minus 20,000 over 100 minus 50,000 over 500. And that way when you divide them, because it's ultimately all you're going to do, you divide them, you then get all these numbers. So take 800, subtract each of those, and the company should have a positive value here. A positive value means that they're going to make a profit in the long term. You know, one policy, if all they do is they sell one policy, you know, for $800 and then they pay out $50,000, that's, you know, not good. But the law of large numbers says that if we sell lots and lots and lots of policies, we should expect that on average, each of those policies is going to bring in this amount of money. Okay, so if they get a negative number here, if you calculate it as a negative, that would mean that they are not selling the policy at a high enough amount, or the payouts with respect to the probabilities of those is not chosen well. Then, all right, so B, what if the company sells 100 policies? How much should they expect to make? Just simply multiply that number by 100, you get $38,000. So this is representing the expected value of one policy if we sell enough of them. At some point, it all kind of balances out, and the company is going to have payouts of 6,000 and 20,000 and 50,000. But if they only do it as often as what this says, then in the long run, that is what each policy can be looked at as bringing in. All right, so question 7. Last question that we have here is about odds. If you're gambling here, there's a phrase that would be odds on that we get to, something called the odds on. All right, now to actually calculate a bet and your winnings, you need to know how to set that up. All right, so what we're going to look at is an event of rolling 2 dice, rolling 2 dice, and the sum being less than 7. Okay, so the table already here has all your sums on it. You have the 7s in that diagonal, and then all the bigger numbers here. So we're looking at 6, 5, 4, 3, and 2 as the numbers. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You have 15 options that would be values that are sums less than 7. Okay, so it says find the probability of rolling a sum less than 7. That would be 15 out of a total of 36 that we have, which does reduce down to 5 over 12. Okay, question B. What is the probability of not rolling a sum less than 7? Well, if the probability of rolling a sum less than 7 is 5 out of 12, then not doing that needs to be the rest of our options, which will be 7 out of 12. Okay, now you can still get it from here, and that would end up being 21 out of 36. But look, these two answers, they have to add up to one whole. So however you've got it presented, just take the difference between the numerator and the denominator, and that gives you your next numerator. So that's it. All right, now why do we ask you to find those two questions? Because when you start setting up the odds for these problems, you need to know both of them. Okay, so when you're asked to find the odds against rolling a sum, oh, my paper got cut off here. Less than 7. That part got cut off. There's another part down at the bottom. If you end up reading real close, you'll notice it got cut out. Something about Google and Word not being as compatible as it needs to be. Anyhow, the odds against rolling a sum less than 7. To do that, you need to take the probability of not divided by the probability of. Okay? So the one of not getting what we're interested in needs to be the numerator. You got to make sure that you put that one in the numerator, the one that's the not. So we're going to have 7 over 12 or 5 over 12, or 5 twelfths, whatever. Now, a neat thing about this, because the denominators are the same, and no matter how you do any of these problems, they're always going to be the same denominator because you either reduced or you didn't. Once you have once you see that you have the same denominator, they just cancel out. I'm not going to walk through all the mechanics of this, like how do you divide fractions and reciprocals and all that, but there's an algebraic way of describing all that. I'll just tell you that they're always going to be the same number and they're going to cancel out, so let's just move on. All right, so the odds end up being 7 to 5. Not 5 to 7. They need to be 7 to 5. Okay, the odds against are going to be 7 to 5. There's another thing called odds 4, which would be the reciprocal of that one. All right, and the reason that we really want to make sure that we set this up correctly is when you get a follow-up question about making a bet. If you have this set up correctly, like not the reciprocal of, so if you got 7 over 5, what you can do once we set up a bet is you can place your bet in the bottom of a proportion. So we're going to take those odds 7 to 5, and then your bet can just go in the bottom spot. If you have this upside down, 5 over 7, and then you put it there, it's all going to get mixed up. So as long as you got your odds against set up correctly, then you can create a rule that says just put your bet down here. Okay, so let's say that we make a bet of $25 and this event happens, so you win. You can put the 25 here. We can just do cross products. We'll multiply the 7 by the 25. We'll then divide that by 5, and that's what I wrote down here. 7 times 25, 175, and then 175 divided by 5 will give you 35. I don't know that part is mental math. I just know the answer is there. You can also do it by quick factors if that's available here, like 5 times what gives me 25? So 5 times 5, and then 7 times 5 will give you 35. Okay, so the 35 is what you're going to win. Okay, but look close at how the questions will be asked. How much money will you be paid? Okay, so the way that gambling technically works is you have to give them the money first. You have to give them $25. Then if you win, you get your winnings plus what you handed them as your bet at the beginning. So technically the final answer is not going to be 35. It's $35 in winnings, but you are going to get paid back 35 plus 25, which is $60.